So today we'll see another application for partial differentiation. That is, we can using partial differentiation calculate maxima and minima function of two variables. So you have already in your 12th class have studied how to calculate the maxima and minima of a function of one variable. So how you started with that thing? Suppose you were given some function f of x, so then you go and you calculated the first derivative for that function, substituted the quantity equal to 0, and then you calculated all the possible points x from that expression. So now these are the possible points where you could either have maximum value or the minimum value of the given function. And to check whether you have the minimum or maximum value for the given function, what you did earlier was you calculated the second derivative and you checked the sign for this derivative. If this appears to be greater than 0, so that means at that point you have the minimum value, right? And if the second derivative has the value less than 0, then you would have a maximum value there. So similarly, we can define the maxima and minima for the case of function where we have two variables. So here your function would look like something like this, f of xy, right? Where we are saying at the point a, b, this function would have maximum value when, suppose these are the coordinate x's, right? And you have some function of this kind. So at this particular point, so here the function will have the maximum value here. Suppose this point here is AB, right? A and B, and we also require some z axis, right? Okay, because we are in 3 dimensions now, because one axis is for x, one axis is for y, another axis is for the function's value. So you require 3 axes here in order to draw the graph. So basically what I'm trying to say is, for the peak value at the point a, b, so the function's value here would be maximum whenever its value is greater than all the neighboring values. So that is what we are saying. The value of the function at this point would be greater than all the neighboring points, where what is h and k, they are very small quantities. So this is the condition for the maximum value. And hence you can rearrange this equation. So you can shift this term to the right hand side. So you will have this quantity. So this is the definition for a function to have a maximum value at some point a comma b. Similarly for the minimum value, suppose you have something like this. So at this particular area, the function's value at this particular point, say this point is a, b. So the function's value here would be less than the function's value at all other neighboring points. So that means in this case we have this condition with us. So next, this is the definition for a function to be minimum or maximum. So this is very simple. So next, let us see what are the conditions for extremum. Now what is this term extremum? Now in order to define this to be maximum or minimum, we call this to be the extremum. So that means when you don't know exactly whether you are having some minimum or a maximum value, then you call that to be extremum. Okay, whatever value is that is extreme value. So this is the general term to represent both the maximum and minimum. So firstly, let us see what are the conditions for extremum. The condition to calculate extremum is again the same. You'll go for the first derivative. Now because your function f, that is a function of two variables, so that means now here in order to calculate the derivatives, you have to take the partial derivative of f with respect to it and x and with respect to y. So these are the first derivatives that you will go and check for. So a function would have an extreme value if the first derivative at the point a, b is equal to 0, and the first derivative with respect to y at the point a, b is equal to 0, provided these partial derivatives exist. So this is the condition. Now you should note that these are only the necessary conditions, but these are not the sufficient conditions. That means suppose you are given the derivative equal to 0, but will the function have extreme value? That is what we are saying. So for that, it is not always the case. You cannot always say the same thing. Suppose for a function these conditions are satisfied, but you cannot conclude that the function should always have an extreme value at the given point a, b. For this, let us see the example. The example is x square minus y square. Now if you take the partial derivative of f with respect to x, so it would be 2x, because y would act as constant, and then the partial derivative with respect to y at the point xy, that would be minus 2y. Now if you evaluate these two derivatives at the point 0 and 0, so you will have these to be 0. So that means the given condition, this one, f of x is 0, f of y is 0, but now we have to check whether this function has a minimum or a maximum value. So for that we use the definition. Using the definition at the point 0, 0, so we have the function's value at the point 0 plus h, 0 plus k, where h and k, they are very small, where h and k are very small. So this thing becomes function of h and k minus the function's value at the point 0, 0. So when you substitute these in the function's definition, so you will have h square minus k square. Now this was your point a, b in the two-dimensional plane, okay, and the point hk, they are the neighboring points. So that means suppose you are taking very small region of points which are neighboring to the points a comma b. So that means you will have some point here, some point here, some point here, some point here. For this, say the h value is positive, and here the k value is say also positive. So here suppose it is 3, 3, right? 3 would be very large. Let's take them to be 0.3, 0.3, 0.3. So at this particular point, the value could be 0.4 and 0.1. So here you see the k and h, they are changing when you are changing the location. So within this particular region. So that means for some values h would be greater than k, and for some points k would be greater than h. So that means this quantity at some points would be positive, at some points it would be negative. So it is not giving you a crisp idea whether your function would be a maximum or a minimum. So that means you cannot conclude from here that the given function would have an extreme value. So this is only the sufficient condition. And moreover, we say it is also not the case that if the function is having extreme value at certain point a, b, then these derivatives, they may exist or they may not exist. The condition is only whenever your derivatives are existing. So that means if your function is this one, mod of x plus mod of y, in one dimension, if your function f of x was mod of x, so what was the graph of this function? It was something like this, right? Straight line. So it would be something like this. So at this point, at the point 0, you have a sharp peak. So that means no derivative exists at this particular point. So similarly, the case is here. Here at the point 0, 0, we know that is an extreme point. Why? Because at this point you will have the minimum value. However, the derivatives f of x and f of y, they do not exist at the point 0 and 0. So this is what we are saying. Okay, so having said that, let us first see how do you find the extreme values. What is the procedure? So suppose you are given some function f of x, y. So firstly, what you do, you calculate the partial derivatives of f with respect to x and with respect to y, and then you equate them to be equal to 0. So that means you will have two equations. So you will solve these equations. So you will solve these equations and calculate the values of x and y. So whatever values you'll obtain, they are known as the extreme or the stationary points. And sometimes they are also known as critical points. So once you have these values, so what will you do? You will calculate the double derivatives. So that means you will calculate A, which is the double derivative of f with respect to x. Then you will calculate B and C, which are the double derivatives with respect to x, y and y, right? At all these points, you will calculate these values. Now, for each point, you will go and check for this relation. What is AC minus B square? So once you see the sign of this, if this comes out to be positive, and moreover your A is negative at that particular point, then you can say that we have a maximum value at A, B. And if this quantity is positive but A is also positive, then you say we have a minimum value at the point AB. So you could remember it like this: for a maximum value A should be negative, for minimum value A should be positive, and this expression AC minus B square should always be positive. If it is negative, then we do not have a maximum or a minimum value at that particular point. And if this expression is equal to 0, in that case we have to further go and look for what is this quantity: f of A plus h, B plus k minus f of AB. So that means we go and look for the definition. By definition, we'll check whether the maximum or minimum exists at that certain point or not. So accordingly, we'll make the conclusions.